Okay.
So, yes, welcome. So the next speaker is David, who's gonna speak about the dense nuclear matter in the course of neutron stars. So David, the floor is yours. You have 30 minutes, 25 minutes of presentation and 5 minutes of discussion. You can start. Thank you.
All right. Thank you very much. First of all, I would like to thank the organizers for this invitation to this nice conference. I like very much the idea of going global and having everybody participating in one way or another. And for me, it's a great pleasure because I also had the chance to be there in EWC a couple of times. So, and visit the group there and all the people in general, the community in South Africa. So I'm very happy to participate. And what I'm going to tell you is about neutron stars. So I've been working on this topic for a few years now, and I will present you what is like the state of the art in the field, and what are the open questions, and of course the perspectives, because it's a field that is been rapidly evolving thanks to the new observations and developments. Okay, so basically I will first say a few words about the question of state of neutron stars, and in the extreme case that there's like the confined matter in the course of neutron stars, I will also start to try to make a connection with the idea of the QC phase diagram, and also I will go on and review a few of the recent developments on the field of multi-messenger astronomy. Especially the most important event, that is the GW170817, and some others that are also complementary, like the measurement of the mass relation of an object by the NICER detector. Then I will present some hypotheses that could help us to disentangle the question whether there's a quark matter or not in the core of neutron stars. And finally, I will say a few words at what's coming up, at what we expect to happen in the following years. So just to have a few words about what is the current idea of a neutron star. So you may remember that neutron stars were first thought theoretically by people like Landau or some other theoretical physicists who just imagined that there could be something like a huge nuclei that would be of the size of a planet or something like that. So basically they were just considering like this idea of a nucleus that will grow, that could be big and just bounded by gravity. So later on there was the discovery of the first pulsar, where this led to the idea, or to the estimation, that the object that was producing these electromagnetic pulses in radio should have the size of a neutron star. That's an object of about 10 or 15 kilometers, something like that. So nowadays, with the current understanding of modern physics and more developments and different types of studies, the idea is that a neutron star is an extreme compact object that can have that can be massive in general, like 1 up to perhaps 2 solar masses, perhaps more, and the radius is about 10 or 15 kilometers. This is very a delicate question, but anyways, so. The idea is that the neutron star is a form of an outer core that where nuclei is arranged in a lattice or in a crystalline structure, and as we try to go deeper into towards the core of the neutron star, we will find that the densities increase, and these increasing densities will produce phase transitions, where the first phase transition that we may find is between this cross that is sort of lattice into the core that is more like a fluid made of protons and neutrons, and perhaps superfluid states of matter and so on. And also there are ideas that there could be these so-called pasta phases, where atomic nuclei get deformed because of the interplay between the Coulomb forces and the extreme pressure that could deform the nuclei. So we will encounter something like this. And then if we go deeper and deeper, there's the question of what's inside. If matter just stays just like a fluid of protons and neutrons, or if there could be something else. For instance, if the chemical potentials of the system are high enough, there could appear some hyperons. These are nucleons that are more massive than the protons and the neutrons, usually with strange content. Or if the density is so high, the question is whether there could be a transition into the confined matter, where the quarks that are inside the protons and neutrons, they are delocalized, or they form some sort of a plasma, and this is the so-called quark-gluon plasma. So these are the questions that we want to explore this, and we will discuss it. So if we just consider a simple rough estimate, let's imagine that a neutron star is like a big nucleus. So for instance, in a nucleus, we can estimate the density of the nucleus if we consider, for instance, that the radius of the atom scales like 8 to the 1/3, that's the atomic number, and then we can come with some estimate of the density given some volume, and we can get some number that will be like the mean density of atomic nuclei, that usually is referred to as nuclear saturation, and this is about 2.3 10 to the 14 grams per cubic centimeter. Now, if we imagine a neutron star that is very compact, of about 10 kilometers, and we put two solar masses because this is the most massive neutron stars that have been measured, about 2 solar masses, and we do this simple exercise, we come to a value of 10 to 15 grams per cubic centimeter. So we see that if the neutron star was homogeneous, then it will have something like 4 times saturation density, which is already something high. Of course, in reality, this density, the neutron star is not homogeneous. It has variations of density. This is what is expected, but this is just a rough estimate to give a scale of how dense are these objects. Now, when people try to model neutron stars, they usually use microscopic approaches or mean field calculations and so on. And since in the laboratory experiments, the data corresponds to values about saturation, then all these models sort of coincide to reproduce these experimental values, but at higher densities away from these measurements, there's a lot of uncertainty. That's why many different models come with different predictions. What you see here on the left side is the energy of pure neutron matter, and below is the energy of nuclear matter, that's symmetric nuclear matter, that, by the way, has a binding energy of minus 16 electron volts in this deep hill at the bottom of this curve. But when these models are extrapolate to higher densities, all of them do not coincide, obviously, because there's no data, or because they have they just give different predictions, and this gives rise to many different types of neutron stars, in the sense that they have different sizes and dimensions. One of the attempts to see if matter is very stiff or is very soft. With the stiff and soft, I mean how much matter can be compressed, or how much matter resists against compression. Has been attempted by looking at the data from relativistic heavy-ion collisions, and back in these days there was some estimate by these people where by looking at the collisions they could try to assess what is the pressure that should be ranges of pressures for a given baryonic density, for instance, as you can see here. The other element that is very important for neutron stars is the nuclear symmetry area, a quantity that has been discussed in this conference already. And basically, if one expands the system of bound nucleons around saturation, but also around x1/2, where x is the proton fraction. So for x equals 1, it's all protons. For x equals 0, it's only neutrons. So if we do this expansion, the symmetry could be related to the coefficients of these expansions beyond the leading term, and but also can be defined as the difference of pure neutron matter minus symmetric matter. And of course, there are attempts to measure this quantity to different experiments, like giant dipole resonances or nuclear masses, what we have here as well here, heavy-ion collisions, so on. And what we see here are the parameters related to the value of the symmetry energy at saturation, and also its slope. This is related to the slope. And well, somehow there's some agreement or some regions of coincidence, But this is at saturation. We also are interested at values beyond saturation that will complete the whole story for neutron stars, and this is one of the challenges. So in a few words, without going too much into details, I will just tell you why this system of a neutron star is a bit special. So it's a bit special because there are more neutrons than protons, and this will lead to some asymmetry that is related to symmetry energy. So for instance, if we consider the total energy of the system, we need to add the component that comes from the bound system of only nucleons, plus a component of electrons or muons, that's the fermions. So the part of the nuclei has to be computed with some sort of microscopical calculations for the nuclear forces and so on. The leptons are sort of simpler because one can consider them just as a Fermi gas of Fermi gas, and it's, for the electrons one can even neglect the mass of the electron is too light. If the muons appear, okay, also the mass has some contributions and so on. So when the total energy is computed, then there are special conditions for neutron star matter, and one of them is charge neutrality. So we expect that the total number of protons equals to the total number of electrons plus the muons, if muons are present. So basically the total charge will be zero, that charge neutrality. And also there's this other condition of beta equilibrium, because inside neutron stars there are beta decays and inverse beta decays, and these two processes should have some equilibrium, and they should behave at the same rate. And this condition is related to these chemical potentials. Of course, there are neutrinos involved in the reactions, but for a cold neutron star, the neutrinos just escape, so we don't consider them in the system. So basically, the beta equilibrium will tie the chemical potentials. So with these conditions of charge neutrality and beta equilibrium, we can compute the equation of state that in the end will be a function of pressure as a function of the pressure as a function of energy density. As you can see, the pressure is computed taking the derivative of the energy function once everything is determined. And we have the equation of state. So we want to model neutron stars, so we can consider the simplest case that are the Tolman-Oppenheimer-Volkov equations that are derived from general relativity, and they describe a spherical star. So the way to go is to pick up a central density of a star, use the equation of the state, and get a point here in this mass-rays relation, and then start to iterate by considering another star with a higher density and getting another point in the mass-rays relation, and so on, and get all these kind of curves. This diagram is very important for the neutron star physics. And there's something called the maximum mass. So once all these curves tend to bend down at some point. So the point where this curve bends down will represent the last stable configuration of neutron stars, because beyond this point the star becomes unstable against a radial oscillation. So what is interesting is that this maximum mass depends on the equation of state. So since we don't know exactly the equation of state, we don't know what is the mass of neutron stars, the maximum mass of neutron stars. But now with the new observations, there are some estimates, and I will also talk about it. So the first challenge to rule out all these models of different composition of the equation of state, the first challenge was to support or to create an equation of state that will support the two solar mass neutron star measurement. The first one, now there are a few of them, like 2 or 3 that are about two solar masses. So equation of state that bend down, as I was telling you, for instance, this one that is old on hyperons cannot reach the two solar masses. So many of these models had to be discarded or had to be improved to rule out to fulfill this constraint.
David, are you there? David? Is it my network or David's network that is hanging?
I can hear you, Daphne. I think it's David.
It's David, yeah.
Okay.
Maybe let's send him a message. I think just
He's gone. So he'll probably log in again, hopefully.
okay.
Yeah,
oh
we
no.
can't hear him either.
Yeah. Okay. He's back. He's back. Yes. David? Still freezing a little bit. And you're muted, David, if you can hear. Yes.
Thank you. I will turn off the camera for now. Maybe that will help with the connection. Sorry about.
Yes, it's okay.
So
Please share the screen.
Exactly. So now let me try to, yeah. Now I'm back.
Yes.
Could you tell me what was the last that you heard before this? What was the last slide you saw before I disconnected? Okay, maybe we'll just start from here. Can you hear me?
Yes, we can hear you.
So I was just saying that there was this measurement of a neutron star merger that brought very important information for the question of state, and this measurement was like a multi-messenger astronomy measurement because it was detected in gravitational waves, but also in electromagnetic radiation that was the counterpart, and all this together brought some ideas for the constraints of the equation of state. So basically, when you have these mergers, there's some gravitational wave signal before and after the merger. And in the case of a neutron star merger, this signal that is related to the amplitude of the gravitational wave is sort of extended. In the case of black holes, dies immediately because matter tends to be, I mean, the black holes tend to be completely symmetric, so they don't produce a longer signal after the merger. And moreover, it has been estimated that the merger was not an immediately merge, didn't collapse immediately into black hole, but it was there was some sort of delay. That this is interesting and also very promising for new events, because the information that happens beyond the collapse, beyond the merger before the collapse is also very important for understanding the constituents of neutron stars. So unfortunately, in the case of UW17 or 817, this information was not detected, but there's hope that in new events there will be some detections of the collapse. Nevertheless, before the collapse, before the merger, there was some from the signal one can get some estimations on the masses of the components, some distributions, and these are related to the so-called tidal deformabilities. So before the two stars merge, they feel tidal forces similar to the one that the moon and the Earth exert on each other. And then it's important to try to combine or to look into this tidal deformabilities of a certain equation of state to make a comparison with what was provided by this merger or by any merger. And for that, one way is to use this prescription where one can perturb the spherical metric of the neutron star and get equations for the perturbations, and then finally compute the so-called log number, which is related to this lambda. This is the lambda. This is the tidal deformability of a neutron star. And then one can look in this lambda 1, lambda 2 plots, where lambda 1 corresponds to one component and lambda 2 to the second component. And then what is being found is that the stiff equations of state are away from this measurement, and rather soft ones are the ones that are preferred. Something also very interesting, especially I think for this community, is that since the neutron star radius is determined mostly by the symmetry energy, there are some ideas that the radius of the 1.4, for instance, the 1.4 solar mass neutron star will have a radius related to some tidal tidal deformability, and at the same time, this could be related to the neutron skins, like halos of heavy nuclei, because all this is also related to the L parameter that has to do with the symmetry energy. So I think this is sort of promising. Another of the ideas is that the maximum mass could be like determined by looking at the trajectory of the merger. So depending on the evolution of this merger, there could be a quick collapse into black hole or a delayed collapse. And as I said, there are estimations that it was a delayed collapse, and under certain arguments, the people in this article have come with some idea that the maximum mass of a neutron star cannot be more than 2.17 solar masses. So this is something that can be considered as an estimate, of course, with the assumption that it was produce a black hole, but it's most likely that the remnant is a black hole and not a neutron star. This applies, or what I've been discussing applies for canonical neutron stars that don't have quark cores. But now if we consider stars with quark cores, we can try to look at the QCD phase diagram. And what happens is that there could be a deconfinement phase transition that is also studied in heavy ion collisions in laboratory experiments. And we want to know if this matter also exists in the core of compact stars. And for that, we can introduce one special model that is called the mass twins, and it's related to the specific possibility that the phase transition inside neutron stars is so intense, like there's a huge jump in the energy density. This energy density can be associated with latent heat in phase transitions and so on. If the jump in energy density, if there's a strong first order phase transition, then the mass radius curves will have some break, forming a separate branch that are usually named as the second branch for neutron stars and third branch for these hybrid stars that have the quark matter core. Of course, following the first branch, that will be the white dwarfs in this type of diagram. So we have first and second branches and so on. So if this is what happens in nature, so there could be some observations of stars out there that will be located in the first and second branch. There are many ways to produce these models. I leave here some prescription of a piecewise polytrope equation of state. Then, depending on how we look at, when we consider the transition happens, we will come with separated branches, perhaps about the maximum observed mass, or maybe at lower values. So we call them mass twins because we can find two stars that can be have about the same mass, but with different radius. So they have different sizes. So if one of the observatories measures these two stars that have the same mass with different radius, then with considerable different radius, then it would be an indication that something like that happens in the interior, and that's why it's sort of interesting. For these kind of models, there are regions. What you see here in the green areas are regions where these hybrid stars can be stable, whereas other stars that are canonical will not enter such low radius regions. So this is interesting to point out that according to state-of-the-art physics, it's difficult to have a non-hybrid star in certain regions, and this was pointed out here. Other aspects that I would like to briefly comment is that perhaps there could be a smoking gun for these twins, and one of them is that, for instance, if the star suffers a transition from second to third branch by accreting matter from a companion, or by changing the rotational speed, the central density can change, and then there could be this evolution that will release energy. So if this happens, I have, for instance, looked at models where the jump in between the one twin into the other is maximized, and we see that there's a lot of energy in this budget for something to happen. So perhaps this could be associated with some astrophysics phenomena. And also, if the system is in a binary, there are some observations that there are some orbits that are not circular, that have huge eccentricity. So one of the possibilities that these models could lead to something like that. If the transition happens, then one of the neutron star that suffers the transition can be kicked out, and not enough to be unbound or to be expelled out of the system, but it can still be bound, but create these very eccentric orbits. So there are some ideas following this model. So we're trying to look for smoking guns if this is the case. If we look at the lambda plots that I was showing, now we have different topologies. Before we have just lines for each equation of state, but now since we have the disconnected branches, we will also have some others that will represent only hybrid stars, and the others that will correspond to pure neutron stars. So here the solid lines are pure neutron stars, and these are others that are hybrid stars. There's a specific case that if the transition happened around between the masses of the first and second component of GW17 or 817, there will be different distribution of these lines in the lambda plot. I will skip for now how does this work, but if you want, you can ask me about this. But the thing is that depending on if the two neutron stars are hadronic, or if the two neutron stars are hybrid, or one is hadronic and another is hybrid, then we'll have different lines here, and this could be studied with more observation of gravitational waves. So the other thing is to look at the post merger signal. And in this article, the people have found that if there's quark matter in the interior of neutron stars, there will be a different peak in this intensity of the amplitude of the post-merger gravitational wave, and this could be an indication. So there's hope to at least to probe the interiors. I would like to also say that there are some tension between what is predicted for the neutron star equation of state from pure astrophysical observations and from pure measurements of nuclei, and there seems to be some sort of tension, and this probably can be reconciled if we consider this kind of models with quark star in their interior. And just to finalize, I will also say that more involved ideas corresponds to a richer QCD phase diagram, where maybe there's not only like a first order phase transition that extend down to the lower G region, or low temperature region, where the neutron stars are located, but maybe there's also like a crossover down here. So if that's the case, then the neutron star should have something smooth at the transition, and this will look different. The matrix relations will look different. For instance, here you can see if we the case of the twins starts to disappear if this is smoother in the case of strong first transitions, or if there's another prescription, then this matrix relation look more like hadronic ones. So this is another possibility, and of course brings new challenges. So I think what is coming up is that in the future there will be more measurements. Hopefully there will be more radio measurements, like that will bring some moments of inertia. So for instance, nowadays there in South Africa, the SKA observatory is aimed at doing surveys of pulsars, like a huge survey, and we hope that they could provide not only mass measurements but moments of inertia, and moments of inertia can also help to constrain the equation of the state, because not all of them will fall inside some measured band. And finally, there's also measurements from X-ray that are related to hot neutron stars, and the people also model the cooling. So this information can be also used to try to understand what's inside, not by looking directly, but by looking at these cooling reactions. And with this, I would like to conclude. Basically, there's new information for measurements of gravitational waves, measurements of mass-rays relation, like X-rays, like in the case of NICER that reported a measurement around 1.4 solar masses. If we wait and we see that there's a measurement of a neutron star that is very compact and is about 2 solar masses, then it's probably a hybrid star. We can perform Bayesian analysis to try to see if we can how well these models can perform with observations, and also we can try to look for dynamical scenarios like explosions, energy releases, or any other things that could work as smoking guns. And well, this is still a work in progress. And I think, again, I think Bayesian inference could help a lot once more data is provided by the observations. Thank you very much.
Thank you. Are there any questions to David? Okay, is there anyone who wants to ask the direct question?
Maybe just a comment from me to David, because quite near Cape Town is the array of detectors looking at gamma rays coming from the stars. So there may be some information there which you might find useful, David. So it would be maybe worthwhile just following what's coming out of there. Through Nico, I can send you the name of what the array is called, and so you can log on to the website.
Thank you very much. I think that will be very useful. So now we're at the multi-messenger era where people try to combine all kinds of measurements. So
yes, indeed.
Very useful.
Okay.
Thank you, Krish. There's also other questions on the chat from Emil. What effect do hyperons have on the equation of state and on the maximum value of the mass of neutron star?
Yeah, usually when the hyperons appear, the Fermi levels of the species, Fermi levels of protons and neutrons, lower because they have to be part of the particles that were protons and neutrons have to converted into hyperons. So the Fermi levels determine the pressure of the system, of the equation of state. So basically, since the high Fermi levels of protons and neutrons go down because they are converted into hyperons, then the equation of state softens, and that means that the maximum mass of the neutron stars goes down. So for instance, if we had a very stiff equation of state of neutron stars that will predict a maximum mass, for instance, of 2.2 solar masses, once the hyperons appear, then this new equation of state with hyperons will have a lower maximum mass, perhaps below the 2 solar masses or something in between. Of course, the uncertainty comes on the nuclear interactions. We don't know exactly how the hyperons and the nuclear protons and neutrons, how they interact, how strong is this interaction. So basically, the main idea is that it softens, unless the interaction is so repulsive that can compensate for this softening on the changing of a species. But in general, it softens and lowers the maximum mass.
Okay. Thank you, David. Is there any other question? If not, thank you very much for